All right. Hey, good morning, class. Mr. Bean here. AP Physics. This is going to be lesson 8.8, Kirchhoff's circuit law and Kirchhoff's circuit theory. And this will be the last part of the class here, talking about circuit analysis. So here we have some ideas here. So the main focus here is there will be two kinds of circuits we'll be looking at. One's called a series circuit. The other one here is called a parallel circuit. When you have resistors in series, or you have resistors that are in parallel. And this here are some examples of Kirchhoff's circuit laws. All right, let's go to part 2 here. This one here is called Kirchhoff's first law, or his current law. I'll let you go ahead and read it here, and it's best explained by an illustration. So let's go to our circuit here. So here we have a series circuit here. Here's a 9-volt battery. Here's a resistor, and resistor. And let me go ahead and let's annotate this. So we'll call this resistor 1. This here we'll call this resistor 2. And we'll call this here resistor 3. So Kirchhoff's current law says this, basically. So let's measure the current leaving here. So the current is 0.3 amps, okay? So here's a junction right here. How much, there's 0.3 amps going in here, and how many amps coming out? 0.3. Okay, how many 0.3 going in, 0.3 coming out, 0.3 coming in, 0.3 coming out, and then going back into the battery, we have 0.3 amps. All right, so the charge cannot be created or destroyed. So Kirchhoff's current law is whatever current comes in, the amps coming in must be the total amps coming out. All right, that's Kirchhoff's current law. We hit pause. All right, and again, to sum up Kirchhoff's current law, here's a node. All the current coming in must equal all the currents going out. So according to this, algebraically, we have I1, I2, and I3 plus negative I4 plus negative I5 equals 0, or we could bring this over to the other side, and this has to equal that. Now, the next thing we'll take a look at here is what's called, hit pause here. The next topic here is Kirchhoff's second law, or his voltage law. I'll let you go ahead and read this here. And again, the best way to, again, here's a 9-volt battery in series. There's a resistor 1 here, there's resistor 2, resistor 3. Now, each of these have a voltage, okay? And let's go ahead and take a look and see how we might illustrate this. So here's a 9-volt battery. We see conventional current flow is going like this. This is a closed loop here. So let's go ahead. So this is a 9-volt battery. So let's go ahead and measure the voltage here. So the voltage here is 3 volts. Okay. The voltage here is also 3 volts. And the voltage here is also 3 volts. Okay. So what we have here then is the voltage across here is 3 volts. Voltage across here is also 3 volts. And the voltage across here is also 3 volts. So 3, 3, 3 equals 3 plus 3 plus 3 equals 9 volts. So the voltage law is the total voltage. Okay. This is best. This is a lot easier to understand it. This could be like V1 plus V2 plus V3. And this here is saying that this is 9 volts. 3 volts plus 3 volts plus 3 volts equals 9 volts. And this is Kirchhoff's voltage law for current flow in a closed loop. Okay, I'm going to hit pause. Okay, so continuing on here is, again, with Kirchhoff's circuit laws. Now, we're going to take a look at series circuits here. Now, here are some relationships that we're going to be using. It says again here, current law says the current going through each node is so all the currents are equal to each other. So current going in equals current going out. The voltages we saw all in a loop all add up to the total voltage. And here's resistance, resistors. When you have resistors in series, you can add them up by R1 plus R2 plus R3 has to equal the total resistance. So this applies for a series circuit only, okay? And we may need to use this a little bit later here. So let's go take a look at a problem here. Let me go ahead and do V here. And let's go ahead and just put this down here at the bottom in case we need to use it. And let's take a look at 12.26 here. So a 3 ohm resistor and a 6 ohm resistor are connected in series in an operating circuit. If the current through the 3 ohm resistor is 4 amps, what's the potential difference across the 6 ohm resistor? So in order to do this here, we probably should kind of draw a resistor here, and let's draw a resistor here like so, okay? And maybe we'll call this resistor 1, we'll call this here resistor 2. So what do we already know? So we know that this one here is 3 amps here, okay, that's 3 amps here, and we know that, we know that this is 3 ohms here. Okay, we'll put 3 ohms here, and this here is 6 ohms, like so, okay? And we do know that the current flow is across this resistor here is given to us as 4 amps, 4 amps. That's coming into here, and we know that 4 amps is also leaving here as well. So 4 amps here, 4 amps here. By applying this relationship right here, we know that there is 4 amps coming in here as well. And we also know that there is 4 amps leaving here as well. So 4 amps going in, 4 amps going out. So we can use Ohm's law here. V equals IR, like so. And we're asked to find the voltage. So the current going through is 4 amps here. Okay. And the resistance is 6 ohms. Okay, I need to write better here. So the total voltage is going to be 24 volts. Okay, all right, take a look at that. And you guys try 1227 while I take a pause here. Okay, 12.27. Hopefully you got 2 amps as the answer. And if you weren't too sure about it, let's take a look here. So we have, here's a node right here. So we have current coming in here, here, and here, and exiting here, here, and here. So we can apply the current law, Kirchhoff's current law, and we can say that we have here a 3 amp current plus a 2 amp current plus this unknown here, which we don't know what it is, it's right here, has to equal 4 amps, which is leaving, okay? And we have here 1 amp, okay? And then we have here 2 amps, okay? And we can apply some algebra here and solve for X. And if I do it correctly, X should give us 2 amps as the unknown current coming into the system. So current going in, total current going in must equal total current going out. Okay, all right, so let's go ahead and take a look at a more complicated, well, it's not complicated, well, slightly more complicated circuit. So here we have a series circuit. Let me go ahead and get here. And we have a 12-volt battery, so we're going to have current flow going in this direction here. So it's always good to identify current flow. And maybe we'll call this resistor 1, call this here resistor 2, and we'll call this here resistor 3. So this is called a verb table. Voltage, current, resistance, power table. If you can do this, you can solve any problem in AP Physics 1 using the verb table, and also in conjunction with Kirchhoff's voltage and current laws. So the first thing we want to do here is go ahead and write in here everything that is known. So here we have a 12-volt battery, so we know the voltage is going to be 12 volts here. That's the total, okay? That's known. And nothing about current yet, but we do have some information about resistors. Resistor 1 is going to be 2,000 ohms. We'll go ahead and write in here 2,000 here, like so. So there's 2,000. The resistor 2 is also 2,000. Okay, 2,000. And resistor 3 is also 2,000. Okay, and then this is power, and power is equal to current times voltage. Okay, so power is going to be the brightness of a light bulb, if you will. Okay, there's power. Okay, so PIV. That should be an I there. And we'll go ahead and pause here, but you get caught up. Okay, so we filled in the table with what we know, and now we can maybe start applying Kirchhoff's laws over here. So okay, here we have equivalent resistance. So it's in a series circuit, so all the resistors add up together. So the 2,000 plus 2,000 plus 2,000 gives us 6,000 right here. So there's 6,000 we can go ahead and put in here, okay? And we also need to use Ohm's law too. V is equal to IR, okay? All right, so no information yet about current, but we might be able to get it by using Ohm's law. Here's 12 volts, here's 6,000 ohms. So we might be able to solve for current by taking 12 volts and dividing it by 6,000 ohms. So let me go ahead and do that on a calculator. So 12 divided by 6,000 equals 0. So here's 0.0, right? 0.02 amps here. Now, because this is a series circuit here, notice this relationship right here, that all the currents going in must equal current going out. So this whole thing here is also 0.002, 0.002. Okay, so we have that here. Let me get paused and let's get caught up. And so now we can go ahead and also maybe fill out this column here by using Ohm's law. So voltage is equal to I times R. So I times R, so 0.002 times 2,000 gives us 4 volts here, 4 volts here, 4 volts here. And using the Kirchhoff's voltage law, 4 plus 4 plus 4 equals 12. Okay? Now over here is power is equal to I times V. So here we have an I and we have V here. So we can just, multiply straight across here, I times V. So 0.002 times 12 gives us 0.024 right here, okay? And this is also 0.024, let's be careful here. 4 times 0.002 gives us 0.008. 008 here, okay? 0.008, 0.008, okay? And 0.008 plus 0.008 plus 0.008 gives us 0.024. And this is how we do an analysis for a series circuit applying Kirchhoff's current laws and the verb table. So this will end part 1.